Soumya Ganguly is pursuing his PhD in University of San Diego, and he's giving his talk on the second session of the mini series on Cheng's conjecture. And I hope you will all enjoy just like you enjoyed the first session. And welcome, Soumya. And I hope you're enjoying sharing your ideas and thoughts too. Thank you, guys, and all the best. Please enjoy.
Okay, so should we start? Should I start?
Yes, please do. Please do.
Okay. So so today we are so last time, if you remember, we actually talked about manifolds and differentiable maps between smooth manifold, and there we talked about diffeomorphisms and relevant concepts. So uh, today we are going to start from the next section, and today we might do a lot of differential geometry. So before I start, can you please confirm whether you can see my OneNote screen or not?
Not yet, sir.
Okay. Can you share now? Can you see now?
No, sir. Yes, it
You
is
cannot,
visible now, sir.
it's visible, right?
Yes, sir.
Okay. So now, today we will talk about first about vector bundles. This talk would be really just touching a lot of things tangentially. I mean, that's like scratching the surface of a lot of concepts. I will try to give you the intuitive idea of everything, but let's see how much we can digest it. So what is a vector bundle? So first of all, we talked about manifolds in the last session. Now we will talk about manifolds on manifolds in some sense. So what do you mean by that? So for example, vector bundle is a very common thing that we deal with in mathematics, and there is a reason behind that. The reason is basically, especially in complex analysis, last time we saw somebody asked a question in the end, and I said that a bounded entire function, which means a bounded function which is analytic in the entire complex plane, is actually a constant. So by similar argument, actually, one can show that any holomorphic map on a compact manifold, we don't have to know the definition of compact manifold right now. It basically, you can think of like a bounded manifold, which is like a bounded set and closed set. So if it's a compact manifold, in that case, any compact manifold doesn't have a global analytic function on it. It becomes a constant by the exact same logic because of Liouville's theorem. So now, because of that, we don't have many functions, global functions on manifold, which are holomorphic. So what do we do? So suppose M is a manifold, a holomorphic function F is a map from M to C, which obeys the Cauchy-Riemann equations locally. But the question is, then if we know that if M is a compact manifold, then we don't have a global holomorphic function other than the constant ones. Then how do we study a manifold? So there are different kinds of functions on manifolds. Now, for that, we need to introduce the concept of vector bundles. So suppose M is a manifold here. Now, you will see that why am I drawing the manifold as a line? So M suppose is a manifold. A vector bundle, if you can think of the vector bundle as a sheet over this line M. What do you mean by sheet? So suppose V is a vector bundle over M, it means that for every point P on the manifold M, you have an entire vector space above the point on the sheet, which means this would be some Rn over the point P. Basically, what do we mean by that? It means for every point P, there is an open set U on M such that on the open set U, you can restrict this part of the vector bundle, which is nothing but a manifold for now, and it will look like U cross Rn. So basically, locally, because we talk about manifolds locally a vector bundle is nothing but a local subset of M crossed with a Cartesian product with some sort of a vector space Rn. This is for obviously, this is called a n-dimensional, or rather, sorry, not n-dimensional. It's called It's a real vector bundle. Okay. Now the thing is, there are some conditions that we need for this manifold V. V is also a manifold. A vector bundle is a manifold. Now, for it to be a vector bundle, we need some more conditions. Basically, the conditions mean that if you have a point P, again the same thing as manifolds, and if you have a point Q, then you know that around the neighborhood of this point Q, you will look at this part of the manifold, and it will look like V cross Rn. Let's draw it with a different color. So this part of the manifold. Then, because there is an overlap here, you can do a transition from this part to this part in a smooth way, in an invertible way, in terms of the vector space part, which means when you are transitioning from this part to this part, you are transitioning by an invertible map on the vector space Rn. Anyways, these are really just technical definitions. We don't have to get into the technicalities right now. It basically, vector bundles for now basically means the manifold, which I mean a manifold on another manifold, where locally it looks like a subset of the base manifold. This M is called the base manifold times some Rn. Now, the thing is, and obviously because you have a vector space structure on the locally on the vector bundle, so you can also talk about sub bundles. And what are they? They are basically the, suppose again you have a manifold M. Now you had a vector bundle. Oh, sorry, I'm writing two things by V. Sorry, let's call this something else. Let's call this W. So suppose you have a vector bundle V here, then a vector subbundle V tilde would be another sheet like this, where for every point P on M, Vp tilde, which is basically, I'm writing the following. Vp tilde is the following. Suppose for every point P on the manifold M, or rather, let's draw it here. So every point P on the manifold M, you have a projection map pi from the vector bundle to the manifold, which actually collapses this entire vector space on this point P. This is a projection map. It's a surjective projection map. So then Vp tilde is nothing but pi inverse of, so for example, there would be a similar projection map because it's another vector bundle, pi tilde. So pi tilde inverse of P will be a vector space. It's isomorphic to a vector space. That would be a subspace of Vp, which is pi inverse of P for every P. In that case, V tilde is a subbundle, which is basically telling you that for every point P on M, the vector space above it for the manifold V tilde is a subspace of the previous vector space we had for the manifold V. Now, this is nothing but a subbundle. Now, there is something called section of a vector bundle. So, what is a section? Section of a vector bundle means, so again, let's go back to the original picture. We have a vector bundle V over a manifold M, and you have a projection map pi. A section, so suppose you have an open set, you have a point P and open set U. So S is a section on U. So it basically means a section of V on U if on U you have, so S is a map from U to the vector bundle V, such that pi composed with S of X is equal to X for all X in U, which means that it is really like a right inverse to the map pi. Now, these sections are very important. Why? Because previously we explained that on a compact manifold, in compact complex manifold, you cannot have holomorphic functions like this. They become constant functions because of essentially Liouville's theorem. Then what do you have on manifolds are basically you have this. So M is also a subset of M. So you can have global sections of the vector bundles like this. So S, if you have a section of a vector bundle V, so V is a vector bundle on M with a projection map pi, and you have a global section, which means for any P in M, you have pi composed with SP is equal to T. Then this is a map, if you think about it. Pi, then S is a map from M to V such that um, it is actually a map from a manifold to some other space. Previously, we had a map from the manifold to the complex number, which is holomorphic. And we know that such functions become constant if the manifold is compact. However, you can have a map, even if M is compact, you can have a map which is like a section, not a holomorphic map. This is not C. This is a vector bundle. So that is why you can have these kind of maps on compact manifolds, which will not be constants. That's why often sections of vector bundles are ways to characterize a manifold. Sections of vector bundles will tell you how the manifold in some sense looks like. Because in the previous lecture, we said that in higher mathematics, we often try to envision something by looking at the maps on it. So in that case, sections are basically those maps that will tell you how the manifold look like. So now we are talking about a lot of abstract things here. Let me give you a concrete example of a vector bundle, which is the tangent bundle. So what is a tangent bundle? Well, it is really something that you know. So the tangent bundle for a manifold M is basically an ordered pair xy, where x is in M and y is in Tx of M. Now, what do you mean by Tx of M? It is the tangent space of x, sorry, of M at x. Now, what is meant by that? Well, there are many ways to, like, it is really what it means what it means by the language. What is a tangent space? So suppose you have a sphere, which is our manifold. If you have a point x on it, a tangent space is really the plane that is the tangent to the sphere at the point x. So this is Tx of M, if this is our M. So now, basically these vector bundles is basically the collection of all the points on the manifold X along with all the tangent spaces at those points. It is a, now it will also give you why it is called a vector bundle, because you are like joining a bundle of vector spaces together and making a manifold out of it. So how does it look like? So let me try to draw a picture so that you understand how does a vector bundle look like. In fact, probably more than drawing, if I show you some computerized drawing, that is probably easier. Let me try to show you something. Yeah. So look at this picture here. Is the picture visible? Can anyone tell me?
Yeah.
Yes.
So look at this manifold. This blue manifold inside is basically the circle. The circle is also a manifold, right? Because it locally looks like real line. So it's a manifold. Now, on every point of the manifold, you are drawing all the tangent lines. Then you get a collection of all the tangent lines on the circle, which if you draw them properly, because this is not drawn properly, I mean, you have to draw all of them, it will become a manifold itself. All these red lines together will make a manifold. And that is the tangent bundle at that point. It is a vector bundle, right? And another very good example to visualize is this. Suppose you have another circle. You can draw the tangent space in a different way. Suppose you are embedding the circle in R3 now, and then you can think of the tangent lines to be perpendicular. I mean, how should I say this? I mean, these are also tangent lines, right? These vertical lines, red lines are also tangent lines to the circle if you are embedding the circle in R3. In that case, all these tangent lines, if you draw around the circle, it will make a cylinder. And that cylinder is basically the tangent bundle of the circle. Here we had the tangent bundle in R2. Here we have a tangent bundle in R3. Anyways, so now, the point is, what is the dimension of the tangent bundle? Tangent bundle is a manifold, right? Because vector bundles are manifolds. So if M has dimension n, which is our real dimension, then Tm has dimension 2n, which is also the real dimension. You can think of it like this. This one dimension is coming, so 2n is basically n plus n. One n is coming because of all the points in n. Another n is coming because of every vector space at that point. For every tangent space at a point have the same dimension as the manifold, which means if M has dimension n, then Tx of M has dimension n, which is obvious, which we have seen from like our examples, right? If you have a sphere is two-dimensional manifold, so the tangent space at a point x is also a two-dimensional vector space, which is coherent with the fact that the dimension n here and here are the same. So now, this is tangent bundle. Now, we talked about sections of vector bundles above, right? So, section of a tangent bundle, a section of the tangent bundle is called a vector field on M. So there are many ways to think of. The rigorous definition is the section of a tangent bundle, but there are other ways to define it. The other way to define it is, you suppose you are a two-dimensional manifold which looks like this, or suppose let me just draw like this. Suppose you are a domain on R2. That's also a manifold. So suppose you are a domain on R2. Then a vector field is basically for every point you have a vector. And because the tangent bundle is a manifold, you basically need that as you vary the base points on the set U, the vectors should also smoothly change as you smoothly change the points. So for example, suppose you have a sphere. So here you have a vector here, then it will slowly change as you go from this point to this point. Then as you go from this point to this point, it will again slowly change. Then again, as you go from this point to this point, it will slowly change, and so on. This is like a vector field. Vector field is basically, it's for every point on the manifold, you have a vector, and as you smoothly vary across the points, the vectors will also smoothly vary. Then, it is important to understand. So this is a vector field. Now, vector fields often have another vector fields often, you want to understand what is the differentiability of a vector field. So what do you mean by that? Well, for that, we have to understand the modern language of differential geometry. So previously, let's think of a sphere again. I mean, I know my spheres are not really looking like a sphere, but sorry about that. Okay. So suppose you have a sphere, and suppose you want to, this is a point P on the sphere. You want to draw the tangent space, and basically you want to draw a vector field on it. Let's put it this way. So what do you mean by that? For every point on the sphere, I have a vector like this. It's a vector field. And if you have it for all the points, then it's a vector field. So now, what do you mean by having a vector at a point? Because often what happens is, we try to visualize the manifold when it is embedded in some R3. For example, let me try to. Okay, can you see me all? You can.
Yes, I can see you.
Yes.
Okay.
Yes.
So think of it this is a basketball or volleyball, right? So this is a volleyball which is like a sphere because it's a two-dimensional. It locally looks like a plane, So it is like a two-dimensional manifold. But when you are looking at it, you are basically looking at this when it is sitting in our three-dimensional world. So this three-dimensional world is called the embedding space, and this is the embedded object. So in that case, when you are thinking of tangent planes, you are thinking of suppose you have a point here and you are trying to think of a tangent plane. So you are thinking of a plane which is tangent at this point, right? However, often we do not want to describe a manifold when it is embedded in some space. So we want to describe a manifold by itself without worrying about the embedding space. So in that case, how do you do that? How do you define tangent spaces or tangent vectors? Because if you think about it, you can draw a tangent plane only because you are sitting in R3. You have the degree of freedom to go in these directions. If you don't know what is the embedding space, how can you draw a tangent plane? You don't even know where to draw it. So in that case, drawing a tangent plane or tangent space becomes difficult. So in that case, what happens that we have a different notion of uh, this kind. We have a different notion of tangent spaces. So and vector field in that sense. So a vector field is basically, so vector field are tangent, basically at every point you have a tangent vector, right? So now, because it's a section of the tangent bundle, so how do you talk about these tangent vectors if you don't know about the embedding space? Well, if you look, whenever you talk about direction, a tangent vector is a direction, right? It's a vector. But we can also think of the derivative of a function in that direction. So in other words, a direction can be thought as a collect all the data of a directional derivatives of the function in that direction. So what do you mean by that? Suppose you have a function defined on this R2. So suppose you have R2 here, and you have a function defined on this. Now you want to know in this direction how much the function increases or decreases. So in that case, you are only concerned about what happens in this direction. So if you know at a point that if you know the value or to understand the direction at a point, to understand the vector at a point, it is easier because you cannot draw the vector now. You don't know the embedding space. It is easier to think of the direction as a collection of data of all the directional change, rate of change of functions in that direction. Because as we said before, in higher mathematics, we often deal with functions and not the object itself. So to understand the object called direction, we are trying to understand the derivative of functions in that direction. So this is called directional derivative, and vector fields are basically objects that you can act on functions on the manifold. And whenever you act them on a manifold at a point on a function, you will see it will give you the directional derivative of the function in the direction of v. Now this directional derivative, however, does not need an embedding space to define it. So basically, now we have a point P and a vector field V of dimension n. Dimension of a vector field basically means the dimension of the vector space at this point. Then a vector field of dimension n is basically, if you have a manifold M of dimension n, is basically at the point P, Vp will look like directional derivatives, right? So basically some linear combination of these partial derivatives at a point P. And by linear combination, I mean some numbers. These are actually not numbers. These VIs are functions of the point P. They are smooth functions. If these VIs are smooth for every P, then the V is called a smooth vector field and so on. So as you understand, this is really like a vector. only in terms of the only difference is instead of basis vectors, we have these derivatives. Why? Because we think of directions as the directional derivatives. Because again, why? Because for this, we don't need to know about the embedding space. So in that case, we can think of vector fields from now on as objects that can act on functions, because these are derivatives, they can act on functions. So vector fields are objects that can act on functions. Directions are nothing but directional derivatives. So then there is the theorem, which I'm not going to prove. V is smooth if Vf, which is V acting on a function f, is smooth for any f smooth from M to R. Okay. Okay. So now, and also for vector field, we need this property is VFG plus VGF. Now, this is something not new, right? Because this is really the product rule of differentiation. We know that locally a vector field just looks like derivatives. So in that case, this is just the product rule of derivatives. So this is called the Leibniz rule, which is needed for vector fields. Anyways, in fact, vector fields can be defined using this Leibniz rule. So now, and by the way, if f is a smooth function, then this Vf, if you act, this also is a smooth function. So basically, the map f to Vf, this is saying that the map f to Vf is a smooth function. This is a smooth function. This is a smooth function. Okay, this defines a smooth vector field. Now, for example, okay, before we go to examples of this, vector field examples we already have given by pictures. For every point, you have a vector, and by vectors, we mean directional derivatives. Now, before we go to further examples, let me actually develop some more theory. One is this commutator of vector fields. This commutator is not, it is sometimes, okay, it is actually not a very difficult thing. So suppose you have x, y smooth vector fields on M, and f from M to R is a smooth function. Then you can define this object called commutator by, it's also a vector field. So it's a vector field. Again, it will be smooth because x and y are smooth. And how do you define them? To define a vector field, it is enough to define how it acts on functions, right? Because it's really directional derivative. If you know how the derivative acts on every function or every smooth function, then you can uniquely say what direction it is, right? That's why you can exactly know the direction of the vector, hence you know the vector field at every point. So then, suppose you have x, y, you want to define the commutator of x and y. And how do you define it? You define it on how it acts on functions. So f is a smooth function, and it will act on the following way. So note that if x is a vector field on M, then x of f is a function. It's a function in C infinity M, right? Because x is a smooth vector field. So x of f is a function when f is a function. Then again, since it's a function, we can act y on it because it's a function, so vector fields can act on it. Similarly, we can have y of f, which is also a function, then x can act on it. And this difference is basically the definition of x of the commutator of x and y. Now, commutators will become relevant. You might be thinking that why am I defining all these abstract objects? Believe me, by next lecture or by today's lecture, they will become relevant. So now let's go to the next part, which is called the push forward of a vector field. So what is the push forward of a vector field? Well, Push forward of a vector field means the following. Suppose I'm going to, let's talk about surfaces first. So suppose M is a, in fact, it's true for higher dimensional manifold also. Suppose M is a manifold, N is another manifold. We have a smooth function phi in between them. Okay. Now, if you have a smooth function phi, then we know that suppose you have a point x here, which gets mapped to the point y by phi, which means phi of x is equal to y. Then, first of all, we know one thing, that there is a tangent space at x, which is t of x of m. Similarly, there is a tangent space at y, which is t of y of n. The question is, if we have a map from the manifold M to the manifold N, does it really induce a map on the tangent spaces? The answer is yes. And this induced map is basically called the differential of the map. This is really the first order approximation. You can think of the tangent space as the first order approximation of the manifold, because when you are trying to approximate a manifold, suppose you have this, I hope you can see me. Suppose you have this sphere, then to approximate the sphere is a two-dimensional manifold, right? So locally it looks like R2, which is the two-dimensional plane. So the two-dimensional plane is really the approximation, the first order approximation of the sphere at a point. So similarly, if you want to approximate the function phi between two manifolds, the first order approximation would come as a map on the between the tangent spaces. So in that case, how do you define this map that is induced by phi on the tangent spaces? Well, for that we have to know how it acts on tangent vectors. So suppose you have a tangent vector, suppose for example lambda here. So how do you define d phi x of lambda, which is the differential of phi at x? So how do you define this? This should be a vector, first of all. This should be a vector at the point y on the tangent space of n. How do you define that? It will be a vector something like this. Let's call this chi. So chi is this. So how do you define this? Well, think of it like this. Suppose you have a curve on the manifold such that the velocity, which means the derivative of the curve at this point x, which is passing, of course, the curve has to pass through x. Suppose you have a curve on the manifold M such that the derivative of the point x for the curve is nothing but lambda. You can create such curves. Then, because this curve is on the manifold, and the manifold is getting mapped to the manifold n by this map phi, so the curve will also get mapped to a curve on the manifold n. Then what is the derivative similarly at the point y for the mapped curve? The derivative vector is nothing but chi. That is how you define the push forward of a vector field. Sorry, push forward of a vector. So the lambda vector here has been pushed forward by the differential map to this vector chi. Now, similarly, because you can define it on every point, you can define basically a push forward of vector fields. Well, because what is a vector field? Vector field is think of vector fields as push forward of a vector fields are basically vectors at every point, directions at every point. So at every point, you can push forward the vectors using the differential of the map. And thus you get a push forward of an entire vector field. So now, once we have the push forward and everything, we are good to go about vector fields. Now we come to the next very, very important concept, which is the concept of differential forms. Now, here we will give some good examples. So maybe you will like it. Don't worry about examples for push forward and everything, and we will come to concrete theory. I mean, concrete examples of them. Although those examples might be a little bit research oriented, but we will see. You can ask me questions after the class today. So, what are differential forms? There are many ways to define differential forms. But basically think of them as objects that act on vectors. I'm not going to define them very rigorously. Objects that act on vectors and give you numbers. What do you mean by that? Let's, in fact, not only vectors, or rather, okay, let's define differential one forms. Differential one forms are objects that act on vectors and give you numbers. So let's give you an example. Let's give you an example and then try to make you understand. So let's do, for now, M becomes Rn. Unless otherwise specified, our M is real Euclidean space, Rn. It's an n-dimensional manifold. And why am I choosing this manifold? Because locally, every manifold of dimension n looks like Rn. So whatever theory we develop here is kind of applicable to a manifold also, just locally. Just do it locally. So how do you do it? Okay. So a differential one form on manifold Rn is a map from the set of tangent vectors of Rn to R. And what do you mean by that? It basically means for every point P on Rn, you have a map alpha P. If alpha is your differential form, then you have, for every point P, you have a map alpha P that goes from TP the tangent space of Rn at P, to R, such that alpha P of Vp plus Wp, Vp, Wp are basically elements of this tangent space, is alpha P Vp plus alpha P Wp. It's a linear map. Alpha P times C times Vp is C times alpha P Vp, but C is a real number. Okay. Now, how do you think of them? How do you write them? Okay. These differential one forms also make a vector space for every point. How do you know that? Well, like this. Suppose you are an R3. Suppose R3. M is your R3 for now. Then at a point P, you have three basis vectors of R3, X, Y, or Z, and X1, X2, X3. In terms of the different, the derivative notation that we set up for the vector fields, we can think there are three vectors for every point P on this manifold R3. We have these three vectors which are linearly independent. Basically, just think of them as three directions: X1, X2, X3. The three directions are now denoted by three derivatives, nothing else. Now, the question is, how do you define a differential form? Well, I can define a differential form called dx1 such that for all point P, dx1 at P acts on del x1 at P and gives you 1. dx1 at P acts on del x2 at P and gives you 0. And dx1 at P acts on del x3 at P and gives you 0. Basically, these kind of things are called dual vectors. Basically, they are dx1 will only act on del x1 to give you a non-zero value. For the others, it will be 0. Similarly, you can define dx2 and dx3. Basically, dx2 will only act on del x2. It will give you non-zero value. It will give you 1. For the others, it will become 0. So now, let's see how do you play with differential one forms. Suppose you have a vector or tangent vector. This is a tangent vector on R3, right? It's a vector on R3, tangent vector on R3. So how do you write this? This is -1 E1. E1 is 1, 0, 0 plus 3 E2 plus 4, E3, right? E1 is E1 is 1, 0, 0, and so on. We can write it like this. However, now we are in a different notation. Instead of E1, we will write del x1. E2, we will write del x2. E3, this is just a notation, honestly, unless you are differentiating function. Okay. Now, suppose you want to know what is dx2 on this vector here. Okay. For any point. For any point, you can define this vector, and then we want to know what is dx2 of this vector here at this point. So dx2 will act on this vector here. How does it act on that? Well, it's a linear operator, which means it will act on each of these things separately, first of all. Now, it's a linear operator again. That's why these constants will come out. So it is -1 dx2 of del x1 plus 3 dx2 of del x2 minus 4 dx2 of del x3. And now you would use the definition. Dx2 only acts on del x2 as a non-zero value. It only will give you 1 here. It will give you 0 otherwise. So it will become 3 times 1, which is 3. So you see, you had an arbitrary vector. You can replace -1, 3, 4 by any numbers you like. So you had an arbitrary vector at a point, and you know how to use the differential 1 from dx2 on that vector and get a number out of it. We got the number 3 from here. So now, similarly, you can play with these things. Now, the question is, how do you define the wedge product between differential forms? I know this is again becoming a lot of jargon, but unfortunately, this is what we have to go through to understand the future topics in my talk, especially in my research area. And wedge products are something that you will see they have actually they have great applications. We will show them momentarily. Okay, how do you define that? So we will define wedge product first of two one forms. So how do you define them? It's basically creates a two form. What do you mean by a two form? One form, what did it do? One form takes a vector, a single vector, and gives a number in output. So a two form now will take two vectors as input and will give you an output, which is very interesting. It's basically this determinant. Right. So this will be this determinant. And then you see that dxi is a one form, so it can act on VP and gives you a number. So again, all of these entries are numbers, and you can, so basically it's a 2 cross 2 matrix, and you can take the determinant and it will be something. So now, for example, let me again give you an example. dx1 wedge dx2 of, suppose, these two vectors 1, 2, 3, 4, 5, 6. You want to know what is this? Again, just apply the definition. This is your VP, this is your WP. So again, what is the definition? This is dx1, 1, 2, 3, dx2, 1, 2, 3, dx1, 4, 5, 6, dx2, 4, 5, 6. Again, if you do the exercise that we did here, basically see that dx1 will only interact with the first quantity because that is 1 dx1 and will give you something non-zero. It will be 1. Again, dx1 will only interact with the first coordinate 4. dx2 will be interacting with the second one 2. dx2 will be interacting with the second one 5. So 1, 2, 4, 5. And this would be, the determinant will be -3. So it takes two vectors and gives you a number. Now, this concept of now similarly you can wedge n forms together, like n one forms together to get an n form. This is called a two form, because again it takes two vectors and gives you a number. So similarly, you can get n forms by wedging n one forms together. And how do you define the wedge product? Well, suppose you have dxi1 wedge dxi2 wedge dot 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 dxin. So what will it do? It is an n form. What do you mean by an n form? N form means that it takes n vectors and gives you a number. Suppose you feed one, v1, v2 up to vn, n vectors in this. Then how will you give it? How will it give you a number? So it will be a determinant again. I1 v2 dot 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 dx sorry, I1 vn dot dot dot, here would be dx in vn, here dot 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 dx in v1. So it's an n cross n matrix and the determinant of the matrix. Anyways, these are again a lot of algebraic things we are defining here. But now things will make more sense. Why? Because now we will study integrals of forms. Now, in case you are familiar with integrals of two variable functions on domains of R2, you will exactly understand what it is going on. Even if you don't, I will try to define and explain it in a down-to-earth manner. Let's try to do that. So if you remember, in one variable calculus, how do you integrate a function? Suppose you have a function on R, or suppose, let's not do it on R. For some interval a to b, you have defined a function f, which is suppose continuous. So f is a continuous function. How do you define the integral? It's a Riemann sum, which means you divide the interval into small strips, calculate the area of each strip, and add them together, right? That is, you calculate integral a to b fx dx. Similarly, if you have a function of two variables, you can think of the function as the following. So you have two variables x and y, and the function can be drawn on the third axis, which is like this, right? And there is a domain of definition, which is like on the domain omega in R2, on which this function f is defined. This is f of xy. So now, if you know a little bit of 3D geometry, you know how to draw this, right? So now, how do you define integral of double integral of fxy dx dy on the domain omega? Basically, here you divided the interval AB into small strips. You do the exact same thing. You divide this into small strips. You divide the, sorry. You divide this into small strips. And then, instead of an area, because you are one dimension higher, you calculate the volume of this object. So now you see, you get this kind of a solid object here. This is your solid object. So you calculate the volume of this solid object and you add those volumes and try to take the limit when these boxes here becomes arbitrarily small. And that will give you the integral of the function. It is same as the Riemann sum as we saw in one dimension. It is just divide your domains into small strips, calculate, take the integral, take the Riemann sum of f of xj, yj, delta xj, delta yj, where this is your delta yj, this is your delta xj. And then this would be the height. This is the height. f of xj, yj, where this is the point, for example, xj comma yj. Sorry, it's becoming a little bit messy, but yeah, as this delta xj, delta yj, the limit delta xj tends to 0, delta yj tends to 0 is this quantity. So now, how do you so now I am claiming that this entire formalism of different of integrals of two variable functions can be thought of as some sort of a, I mean, I can write this in terms of differential forms. How? Well, the idea is as follows. Create, write, create a vector like this. Create a vector v j x, for example, as delta xj comma 0. Create a vector vj y as 0 comma delta yj. Then because of because of this calculation that we did here on how differential two forms act on two vectors, you can just check that delta xj delta yj is same as the action, uh, it is same as dx wedge dy on the vector vxj comma vyj. You can check that. That's a homework for you. It's the same calculation that we did above. It will be nothing but that. So then you see that this can be written as xj tends to 0, limit yj tends to 0, summation f of xj yj dx wedge dy of vxj vyj. So integral over, now the thing is, if f is equal to 1, double integral of dx dy, which is nothing but double integral of 1, will give you the area of the omega. So then if you put a, now we know this is same as if you put x equal to 1, which means delta xj goes to 0, delta yj goes to 0, 1 times dx wedge dy vxj vyj. So now area of omega can be thought of as a sum over these action of differential forms on two vectors, as a on a Riemann sum kind of way. So now area can be thought of integral or summation of a two form. This is important. Omega was a two-dimensional object because it was on R2. If it was a domain of the function, which is in R2, this is omega. So omega was a two-dimensional object, and then it is in R2, and the area of this two-dimensional object can be thought of as an integral of a two form. That's why, similarly, volume, so now if omega is in Rn, volume of omega is basically integral of a n form on omega. This n form is called the volume form on omega, which was dx wedge dy instead of when we had an omega domain in R2. So integral of an n form on Rn will give you a volume of a subset of Rn. Now again, all this we did everything for Rn or subsets of Rn, right? All these things can be done on a manifold. Why? Because a manifold can be locally thought as Rn. On differential forms, essentially just depend on local data because vectors are defined locally. Vectors are defined, you can think of a point as a point in Rn, and then you can define a direction at a point, which is also like Rn, a point vector in Rn. So all these things can be done on a manifold. Just think of the manifold locally, and you can integrate a form on a manifold, an n form on a manifold, to get some sort of a volume of the manifold. It might be infinite, depending on the cases. Now we know how to calculate volume on a manifold. The question is, how do you calculate length on a manifold? For that, we need the concept of Riemannian metric. So what do you mean by that? Suppose you have a manifold M. For that, on this, we define something called a Riemannian metric G. This is nothing but, so for every point P, you have a tangent space on the manifold. A Riemannian metric will simply give you an inner product, a dot product on the tangent space. Why will it help us to define length? We will see that, maybe not today. So basically, it will give you inner product on TPM for every P. It is called smooth metric if it varies smoothly with P. We are not going to make them very precise. So basically, this inner product value of two vectors on the tangent space, it will vary smoothly as you as you vary the vectors and the points smoothly on the manifold. So now, for example, let me just stop by giving us a trivial example. So suppose you have Rn is a manifold, right? So you can think of the Euclidean metric, the Euclidean dot product. It is also a Riemannian metric. How? Because any vector on Rn or a tangent vector on Rn can be thought of something like this because of derivative culture. Then suppose you have another vector and you want to take their dot product for every point. How do you do that? Well, just in the usual way of taking dot product of two vectors in Rn. So then this dot product defined in this way is called the Euclidean metric, which is the metric on which the Euclidean geometry is dependent on. And there is one important point: every smooth manifold has a Riemannian metric. Okay, so this is something that we are not going to prove. The proof is a bit involved. However, this is the point up to which I think we should cover today. Let's talk about how, by using metric, you can define length on a manifold, length of something like distances on a manifold next time.